Welcome everyone at our machine learning course. I hope you are well and healthy. It is unfortunate that we cannot do this course in person. I will do my best to deliver the content and knowledge of this course with online learning. As I explained before in my email, I'm recording these sessions first to avoid technical problems and issues that might happen in live sessions, and also to give you the flexibility to watch and learn at any time. Having said that, during the lecture time, which starts on the 4th of April, there will be no live sessions. Uh, Please use the time to watch these video sessions, and I will be online the whole time waiting your questions. For that, I will create a Google Chat room where we can share the knowledge. You can see the questions by your colleagues, and if one of the questions needs more live session, then I will of course jump in and I will explain to all of you the answer. So this is an introduction lecture. I will cover here the background of machine learning and deep learning, the history of artificial intelligence, some definitions and terminologies, the machine learning tasks, and the machine learning branches. I'll also present the syllabus and how we can assist you in this lecture or in this course. So machine learning is a wide range, and we will not cover everything in this course, and we cannot actually cover everything about machine learning in this course. So which means I'm not covering statistical machine learning or some classical machine learning techniques like support vector machine or Bayesian networks. And also I'm not covering conventional machine visions like low-level pre-processing, edge detection, filtering, and so on. I am focusing on deep learning. So this course is mainly about deep learning because deep learning is now the most common and successful machine learning algorithm, especially when we talk about intelligent transportation systems. Deep learning is the most popular there. So this is why it's our focus. So that having said that, we will talk about deep learning theory, deep learning background, deep learning based machine vision. We'll talk about reinforcement learning, which is uh, becoming very popular now with deep learning together to solve complex problems that haven't been solved before, mainly problems that basically rely on unsupervised learning, not supervised learning. We will also talk about natural language processing, which is about text analytics. Is not directly related to transportation systems or intelligent transportation systems, but it's very important, especially the architectures that are used there. I'm talking here about deep learning architectures. They are useful and we can use them in other applications or use cases. So this is a course plan. We will start from the bottom here with the linear regression, which is the basic of machine learning. And then we move to the logistic regression, which is a kind of the bridge between linear regression and the neural network. After that, we'll talk about the shallow neural network. Shallow means one layer neural network. We will see what I mean by that later. Deep neural network means multi-layers neural network. After that, we'll talk about the learning mechanism of a neural network, which is a backpropagation. So if you understand these four steps, actually, the rest would be easy to you because these are the fundamental and the basics of deep learning. So the linear regression, logistic regression, the architectures, and the backpropagation algorithm. Now, the rest are kind of new architectures. Not in, Some are new learning technologies, but they all depend on backpropagation. So the convolutional neural network, or what is called the CNN, would be next, which is mainly applied in machine vision. Then we talk about recurrent neural network, which actually process temporal data or time series data or data over time, like signal, like voice recognition, for example, like lane keeping in driver assistant systems or self-driving cars. Then we'll talk about semantic segmentation, which is kind of ecosystem of the convolutional network. It's used to segment input images into different objects based on the semantic. For example, cars, they have different semantic than humans or than pedestrians. They also have different semantic than trees, roads, and so on. After that, talk about generative adversarial network, which is also now recent technology that's becoming very popular. The difference between discriminative models like CNN or RNN or shallow neural network and generative models. This discriminative models, they take data as input or features based on input and predict an output. I will talk about that later. But generative models, they generate data, so they generate feature space, like generating input images or generating human faces. And if you hear about deepfake, for example, it uses uh, GANs or generative adversarial network. So we have 4 days for. It was planned for days, for block days for this lecture, but since we are doing now online learning, it's not necessarily 4 days. As I said, the videos will be online, so you can watch them at any time you like. I will start publishing these videos this week, which is the first week of April, and from then you can start watching these lectures. So, but if you talk about the original plan, we will start by first day it's linear regression, then logistical regression, then shallow neural network, backpropagation algorithm, then something important for training neural network, which is called variance bias trade-off. In the second day, we'll go deeper. We'll talk about the serial neural network, and how to use it for machine vision. Then a daughter of it, as I said, which is the semantic segmentation. We'll also talk about autoencoder, which is unsupervised learning-based neural network that actually, so the semantic segmentation is kind of actually the daughter of CNN plus autoencoder. We'll talk also about the mask CNN, which is a specific type of CNN, which improves the object detection performance. The next day, which is day 3, would be about temporal based machine or deep learning, which means processing time series data. Here we talk about recurrent neural network, but not only time series basically, it's also called the, so for example, sequential data set, like text, for example, because the words are sequential. So we have recurrent neural network, we have the LSTM, which is a specific type of recurrent neural network. We'll talk about natural language processing here, because as I said, RNN and LSTM are used also for text recognition. We'll talk about transformers and attention mechanism, which is also very popular now. And therefore, I'll talk about reinforcement learning. So therefore, it's more like about recent technologies, very trending technologies. They don't have yet any, or they do have, but not that let's say popular in terms of real life applications or practical applications in real life systems. But in terms of technology, they are very interesting. They are very actually promising. Here I talk about the reinforcement learning, deep reinforcement learning, which used to win AlphaGo or to win Go game again against the Go master or the best human Go player, and also talk about the generative adversarial network or GANs. So the history of artificial intelligence, and so machine learning is a part of artificial intelligence, and deep learning is a part of machine learning, as I'll show you later. And artificial intelligence is not something new. Recently, we are hearing a lot about it. It's very hype now, but it's not new. Actually, it started in 1943, which the foundation of artificial intelligence was established. And in 1950, we had the first game actually, so AI playing checker games against humans. In 1955, we had Lisp, which is a functional programming language for AI. Then the first AI MIT lab was founded in 1959. Then in 1964, we had the first chatbot. So chatbot means a robot that can chat with humans, which is Elisa, which started in 1964. In 1974, the first autonomous car, so autonomous vehicles, not that also new. Now they have, of course, much better performance, but the idea of autonomous car is not new. In 1980, the backpropagation algorithm was introduced, which actually was kind of turning point for neural network and artificial intelligence in general. In 1985, it was the first autonomous vehicle using neural network. So this is because of the backpropagation. We could now start train neural networks. And this was in 1985. It was the first autonomous vehicle using neural network. Then we had the first convolutional neural network, which also was a second turning point in deep learning, because now we can process images. We can do basically machine vision using neural network. After that, in 1997, IBM Deep Blue, which also won the chess against the human master in chess. Then in 2011, IBM Watson, which also was basically from IBM. It doesn't use deep learning or machine learning. It uses knowledge graph and symbolic AI, but it was also very successful against human. Then in 2012, also another turning point in your network or in deep learning, where we could train your networks using graphical processing units or GPU. In this way, we could actually have more than 1,000 times faster training with much bigger data. And after that, we started really see a different trend in terms of number of new applications, number of new milestones that are achieved with artificial intelligence and the neural network. In 2016, we had the AlphaGo, which won the Go game against the human master as well. And Go game, if you don't know it, it's much more complicated than chess. So basically, and starting from 2016, we started to see many applications, and so mainly in the self-driving cars, we use a lot of neural network there, a lot of deep learning there. But also we see it in voice recognition systems like Alexa, like Google Assistant, for example. We see it in machine translations in Google Translate. Google Translate has changed a lot since I think for the last 10 years because of deep learning and machine learning. The performance actually was much improved using deep learning, and more technologies, more applications are actually introduced every day, and many new architectures, new papers are published every day with respect to deep learning and machine learning. So as I said, AI, and as I said, machine learning. So where is machine learning and where is AI? So artificial intelligence is a kind of, let's say, the title or the big title that covers or contains many technologies inside. So starting from so artificial intelligence in general and machine learning also, they all deal with data and relies on digital data. So starting from the first level, which is data analytics, which is mainly statistics, data visualization that are done by humans. So we take data, we manipulate the data, we try to do some statistic on them, draw some graphs, and try to get some insights. Now, after that comes data science. Here means basically where we start to automate some of the tasks that we do in data analytics, like we build regression models, we build some predictive models using data science. After that comes what is called the representation learning out of data. Here we start to go into direction of automated learning and machine learning, which means how to represent patterns, for example, in the input data, how to do automatic feature extraction out of the input data. If you are if you are familiar with traditional machine vision, we usually extract features. We try to detect features for certain objects. Then we use some kind of let's say mapping function to map these features to different categories or different classes. The idea of representation learning is basically automatically feature extraction. And deep learning is basically, it's called end-to-end learning. So it starts from raw data and do the feature extraction. It does actually high-level feature extraction, which means not only one layer of feature extraction, I will see later, it's multi-layer features, starting from low-level features to high-level features. And also it has, of course, the reasoning part of it, which actually reason about these features and do the mapping. After that, we have machine learning, which, as I said, it includes deep learning, but include other technologies like support vector machines, Bayesian models, decision trees, random forest, and so on. After that, we have artificial intelligence, and here we have basically machine learning as a part of it, but also we have symbolic AI, we have rule-based systems, reasoning systems like semantic net ontologies, knowledge graphs, and so on. So what is the definition of machine learning first? So there are two famous definitions. The first one is basically kind of an abstract. So machine learning is a type of artificial intelligence that provides computer with the ability to learn without being explicitly programmed. What the meaning of that? We all need programs. We all need basically computers or softwares to do tasks, to do automatically some tasks. There are two ways to do that. The first way is to program that explicitly. So to write the rules, to write all the steps that this program needs to take. And this is the rule-based systems. The machine learned systems basically tries to figure out these rules automatically from data. So you just give examples, just give data to the systems, and it tries to learn these rules without being explicitly programmed. Another definition here says machine learning is a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P. It is its performance at tasks in T and basically as measured by P improves with experience E. What the meaning of that? Because we have a lot of EPT, we'll see what the meaning of that by examples. So let's take, for example, here one of the applications, which is basically about recognizing spoken words or voice recognition, like Google Assistant, like Alexa, or other robots. So here we have basically the task is basically to recognize the spoken words. The experience here is the historical data, which includes examples of voice, for example, recorded voices, and the corresponding recognition. Let's say, for example, one of the voice recognition tasks would be to open a door. So you would tell a robot open door, and the robot would open the door. So we have historical data of humans saying open the door with different voices or different frequencies and different amplitudes, and the output would be open the door. So this is basically the experience, the historical data that the machine learning needs. And for example, there's a task, then we have the performance, and the performance is how good the system is. For example, if we have thousands of data points, thousands of examples, the system could recognize 90% of them, which means 90% of them basically the system hear the voice and do the correct action. This is what is a performance. So we have the task to recognize a voice, experience is the historical data, and performance, how good the system is doing. We have the second application, self-driving cars. The task here to either segment the input images into different semantic, like we have here, for example, dog, grass, and tree. And then we have also cars, humans, tree, and buildings. This is semantic segmentation. Or to do lane recognition and lane keeping. This is another task. We have for that historical data. So we have, let's say, millions of images, and these images are labeled. For example, by humans, they are segmented into different clusters or different semantics. And this would be the experience. Now, the performance would be first, for example, when it comes to lane detection or lane keeping, uh, how small the cross-track error is. And of course, here also in terms of segmentation, how good the segmentation is. Let's say if they have here 10 cars and the 10 cars are correctly segmented, this would be, for example, 100% car segmentation accuracy. Another application which is very popular now, it's in medical imaging. For example, we just heard from China that they are using deep learning to diagnose COVID or coronavirus. Just they started with labeling some images and then they started using it to diagnose people. The advantage there using machine learning, it is much faster and sometimes more efficient than humans in diagnosing, for example, some diseases using medical imaging. In robots, of course, self-driving cars is also robots, but here, for example, we have another one which is the drones, the drones control. And we have here the road drone, taking the input scene as an input to the system or to the deep learning system, and try to predict the steering angle and also try to do the semantic segmentation here as we see. But it also can detect pedestrians, for example, so it does multitasks using deep learning. So now we talk about the terminologies. The first one is data. I think everyone knows what data is. When it comes to machine learning, data is very essential. Data sources could vary from sensor data to transaction data to text data, image data, and so on. So sensor data could be, of course, camera sensors, could be IMU, for example, could be LiDAR sensor data, but also could be text. This is basically also data that machine learning deals with. And online on the internet, we have a lot of text, of course. And also transaction like financial data also could be a data for machine learning. In machine learning and AI, usually hear about structured and unstructured data. So structured data is everything that can be organized or structured in tables. Like unstructured is the other way. For example, images are unstructured. Voice are unstructured. Voice data or voice basically signals. Text documents, they are unstructured because they are not in tables, they are in documents. So in machine learning, one of the basically ways to train machine learning models is to go from unstructured to structured. So to, for example, extract some features from the unstructured data and structure them in tables, then train machine learning model. But now what is really, let's say, strong point or strong feature of deep learning is the end-to-end learning, which means you can go from unstructured to decision without caring about structuring the data or extracting feature. The second terminology is the features or attributes. So when system receives a signal or receives an input, it needs to extract some input, some features that describe that input or that sample. For example, if I am doing, let's say, classification between red apple and yellow apple, then color here is a feature that you need to consider. So when it comes, for example, to vision, we have also edges, we have motion field, we have depth, we have all these features that can be extracted from images and they can describe objects. If I'm classifying between cars and humans, then maybe the edges, the curvature of these edges basically are important. In case of voice, for example, or acoustic, we have the frequency, we have the pitch, we have the amplitude of the signal. Also, they are also important features. In case of financial trading or time series, we have historical trends, we have statistical moments that can be used as indicators. So the next important terminology is the decision function or the hypothesis. So we take first the input image, for example, an input signal. We extract features or attributes. Then we need to have the decision function to basically process this input and decide or give an output. And this is basically called the decision function, which is a mathematical model that maps inputs to targets or map inputs to outputs or to classes or to categories. Uh, in case, for example, self-driving car, the output of a decision function is a steering angle. So the function that takes an input, which is basically the input image, for example, of the scene, then predict the steering angle. So this is basically what is the decision function about. So let's take an example here. This is a very famous example in machine learning. It's a house price prediction using the house size. So we have one feature, which is the house size here, and we want to predict the house price. We first hear the experience or the historical data, which is in red points here. This historical data basically has always have the house size as an input and has also the house price and output. So this is the supervised historical data because we have the input and we have the output. And basically what we see here also the feature, which is the outside, which is here is represented by x1. And the decision function, which is this green line, which actually here represented by this mathematical model. So here we have the decision function, the role of the decision function now getting in your input data, which is here the blue point. For example, we get here new input, which means we have a house, we know its size, but we don't know the estimation of the price. So we use that decision function to get the estimation of the price. So now, so having said that, this is the decision function. X1 here is a feature. We have another feature here, the bias, which is always equal to 1. And we have the weights here that basically parameterize this decision function. So talking about weights, talking about parameterization, so we have the training and learning. If we look at these weights here, if I manipulate omega 1 and omega 0, I'm moving this, of course, this line along this space or inside this space. So the learning and training algorithm in machine learning is the optimization algorithm that tends to find the best basically weights or best coefficients like omega 1 or omega 0 that make the function fits best the data. So we need to find the lines that fits best the data, which means we need to find omega 1 and omega 0 that fits best the data. This is basically the role of optimization, and this is what it means by learning and training. We need to, using our training data, looking at the performance P, we need to minimize the performance by finding the optimum weights or coefficients. And then, for example, using the house size and the house price. So training, learning, fitting, they all mean the same. So the next terminology is performance, then the cost or loss, they are also called. And here is the way to measure basically how good the system is or how good the model is. There are many performance measures, as we'll see later. There are sort of performance measures or cost measures are specific for classification, other for regression. But the most basically common one is the mean square error, where we basically estimate the difference between the real or ground truth data point and the predicted data point, and then we take the mean squared of along the data set or along all the samples. The goal, of course, to minimize this mean square error using the learning or using the optimization method. So we need to find the most optimum weight that minimize that error to 0. Next, after terminologies, we have the machine learning tasks. The first one there is classification. Classification is defined as the problem of identifying to which of a set of categories or group a new observation belongs. So, for example, I talked about classification or classification between red apple and green apple. Let's assume that we have here two classes. They have two features. For example, we have the color of an object and we have the size of an object. These red points here, they belong to class A, which means this is a labeled data, this is supervised data, because for each point, we have the color of that point, we have the size of that point, and also we know to which class it should belong. Is it a green apple or is it a blue apple? Red apple, sorry. So this is basically the two classes. We need to build the decision function, which is the classifier here in this case. It's a mathematical model. If I have a new point and this new point, for example, it's a new sample, if it is on the right side of that classifier, then it belongs to class A. If it is on the left side, then it belongs to class B. So this is the idea of classifier, and this is a decision function here. So regression is similar. It takes inputs, features, build decision function, then do the mapping. But the difference in regression, the output is continuous numeric value. So it's not categorical. This continuous like in classification, but it is actually numerical and continuous data. And here basically we model the relationship between two variables or many variables. And here the house price is an example of regression. So it's as classification, but it's not categorical. So time series forecast, it's also task basically, or it's application of machine learning. It is as or similar or actually the same as regression, because here we have first numeric data. We take input variables or input numerical continuous variables, and we try to predict output numerical values. So in terms of time series, we usually take the historical values here as inputs and try to predict the future. Maybe if it is euro dollar rate, for example, we take the historical values of a euro dollar rate. So, for example, for the last 5 days, and we try to predict for the next 5 days. The difference here is basically the output and the input, they are from the same signal, from the same time series, but they have a time delay between the input and the output. Sometimes in time series we can include more than one time series. For example, for the euro dollar, again, we can include also the oil price, the corona infection, for example, curve, and so on, in order to predict the euro price in the future. So after tasks, we have branches, and under branches we have 5 main branches. They are actually about learning algorithm. We have supervised, unsupervised, semi-supervised, reinforcement learning, and deep learning. And recently we got what is called self-supervised that I'll talk about later in. So supervised, an example of that is classification or regression. Supervised means we have input and output examples. So we have images and their labels. Unsupervised is like clustering. We don't have labels. So we have only the input data, and as I said, we can cluster them, we can group them with respect to similarity measures. Semi-supervised is a combination of both. Let's say we have 1 million transactions or 1 million samples. We have only 1,000 of them are labeled. So what to do now is basically to try to train a model on these 1,000 samples, and then try to generalize from this 1,000 over the other basically 900 samples. So only part of the data is labeled, because labeling is very expensive, of course, and because it requires humans looking at images, labeling them. So if we can train on let's say, a subset of this data set that is labeled, and then get a performance that actually can generalize over the whole data set. That's what is called semi-supervised learning. And if you can do that successfully, then of course it's better than supervised, because you don't need to label the whole data set. The next part is the reinforcement learning. It's also unsupervised, but the difference here, it doesn't rely on data. Reinforcement learning is learning from experience. It's basically how humans learn. And the idea here is that a robot, for example, or AI agent, it would interact with the environment. Let's say if it is a game, then we have an agent that's playing chess. Then this agent would try to play some moves, and then if it wins, then it will basically get a positive reward. And if it loses, it will get negative rewards. And then it will change or adopt its policy in order to maximize the reward in the end. So this is basically learning from experience and not learning from data. Deep learning now, it's a kind of a branch. It's basically the end-to-end learning, starting from features extraction, then building high-level features, then doing the reasoning and mapping, and basically supervised, unsupervised, semi-supervised, and reinforcement all can be done using deep learning. So this is basically the end of this session. Next session, I'll talk about linear regression.